Hey, hello there. So this week I'll be solving linked list related questions, and since it's Monday, I will do a short review about the topic of the week. So linked list is the kind of a fundamental data structure for implementing a lot of the abstract data types like a list, a stack, and queues. It's pretty much just a sequence of node objects, and it can contain a pointer to the actual data object it holds. But more importantly is the link that allow us to traversal through the sequence of nodes. If we are looking at singly linked list, the nodes only have a next pointer that points to the next node in the sequence. If it's double linked list, every node will have two pointers, one to the next node in the sequence, one points to the previous node in the sequence. So that's pretty much linked list. And usually we will maintain a head pointer and a tail pointer. That's kind of the alias to the first node and the last node in this linked list. So that's pretty much the linked list, and these are the typical operations you would want to do with a linked list. We would want to add a node to the front, remove the node from front. With the head pointer, we can actually do both of this in constant time. We want to do the push, add a new node to the back, remove the last node. With the help of the last tail pointer, we can actually do the push in constant time. But for popping, for singular linked list, it's order of n, because we have to grab the previous node previous to the last node. We need to have that reference to that in order to do the pop. To remove the link and also update the tail pointer. So that's a log n. That's n time, linear time. If we are working on double linked list, then this pop at the back is also in constant time. And accessing the value a node via the index, looking at the third node or any arbitrary node by its index, it's in linear time. We have to traverse from the head node towards just count how many number of nodes we have seen during the way along the way, and terminate while we looking at the right index. So that's linear time, and for that reason, the insert a new node in the middle has to be in linear time, because we have to get to the node there first, then we can do this insertion. Deletion is the same story. We have to at least get to the the target location inside this sequence in order to be able to perform a actual deletion. The insert and deletions are nothing but just rewiring these pointers, and so that's why they are lower bounded by this accessing index kind of be bottlenecked by this, I would say. So the very last common operation is just swapping the nodes. Given the node I and j by their index, we want to swap this too. It's in linear time as well, because we have to go from the beginning to the i's node and go to the j's node before we can do any kind of pointer rewiring. So that's why this we got a bunch of linear time operations here. Note that this double, the reason we use this is to maintain the sequence of order of those the values, the data objects that it holds. A common usage beyond this linked list alone is to have a hash map on top, and it's pointing to the internal nodes there. So we can use the hash map, hash table, to have random constant access to the intermediate nodes in there. But the node itself is to use as the placeholder, reference holder for the data object, also to maintain the sequential order of this data objects that we care about. We can couple that the linked list with a hash table to get constant access to the intermediate nodes inside here. If we don't couple that with the hash map, we need to traversal from the head along the sequence to find the node we want. So that's That's just the drawbacks by the linked list itself. So some of the common operations on singular linked list. I think most of the questions are targeted at the singular linked list because double linked list, it's pretty much the same. It's just it can go back more freely compared to singular linked list. And a lot of the questions usually ask one pass, so there's no need to go back. So that's why I think most of the problems related to linked list are using targeted at a singular linked list. So here we just have a class for the nodes object. It has two fields, a pointer to the item, a data object, pointer to the next node in line in the sequence. And here I'm just creating 4 nodes and have the previous nodes always pointing to the next. I'll create 2 alias, one for the head node, one for the tail node. So after that, I could actually delete this collection for the nodes, because from now on we're just gonna be able to access the nodes inside this linked list through the head node there. Hate that. So yeah, so that's the creating the definition of a node, linked list node, and creation of a linked list, creating the alias to the head node and tail nodes. The first common kind of operations that we perform on linked list is the traversal through the list. Given the head node, we want to go all the way to the tail. So that's when we create an alias for the traversal, a current node that we are looking at. If it contains a next pointer, that's pointing to something that's not a null pointer, we actually want to move the traversal node to that node. And here I'm just detecting if the next node is nothing, it's a null pointer, I'm gonna create a alias for this current node as the tail node. So it's basically just a while loop, following the links to go further and further. Once we see the next node is the next pointer is pointing to a null node, we create a tail alias to the very last node and just return. So that's the traversal, and we can also count up the number of nodes there. So yeah, to determine the number of nodes in the linked list, there's also a linear time operation. Obviously, this is to go from the head to tail. If we want something that's in middle, we can passing in the index, the k. So instead of a while loop, we can do a for, to perform this following the link for the k times, so that the node we end up will be the case node. We can also do the traversal by checking the node's value. So while this we still have a node to following the link, and its value is not equal to the value that we are looking at, we can just keep doing this traversal, otherwise we'll terminate and return that node we found. So that's traversal. Then it's the push and pop. Push is simple. We just have a new node ready, have that new node pointing to the current head node, and rewire the basically recreate the alias for the head node. So yeah, we'll create a new node and have that new node's next pointer pointing to the current head, and update the head alias to the the new head node, new first node in the sequence. Pop is just to short the link, between the the current head node. So we update the head to be the second, the current second in the linked list in the sequence. So that's pop from the front. So these two, you can see it's we don't do any kind of a traversal, so it's constant time. Push to the back is just add a new node to the have the tail node, the very last node's next pointer pointing to this new node object, and update the alias for the tail. So that's you can see it's a constant time. But for popping from the back, if we are working on singular linked list, we have to traversal from the head to the immediately previous node to the current tail node, so that we set the next pointer for that last to the second to the last node, we set the next pointer for the second to the last node to be a null pointer, and update the tail reference. So that's popping from the back. Since that we need to actually do the put traversal from the beginning towards the pretty much the end, it's a linear time operation. And then we're talking about inserting and deletion nodes in the middle. One thing that it's kind of bottleneck us is to traversal from the head to the eyes indexed location. So we have the head nodes, that's now our starting point, and the counter for how many hops that we need to jump. So for every hop that we jump, we decrement that number. Once it's turned 0, we pretty much find the value, the node. And it's usually useful in terms of a singly linked list to also return the previous node to the node that we found, because in the deletion and insertion we gonna use this previous reference a lot. So insertion is basically just to have the previous nodes pointing to the new node, and have that new node points to the node to the current ice node, and that's pretty much it. So have the previous node pointing to the new node, have the new node pointing to the previous node. So I guess I should change this name to be maybe like current or something. Erase is to short the link, so we have the previous node have its next pointer pointing to the next to the current, so that we pretty much just shorted this current node at the ice location. That's erase. And this in linear time, because we have to do this traversal, so it's a linear time operation. Swap, it's a similar story. We need to get to the ice location and j's location, and also store their previous nodes, and do this rewiring. We can use some temporary variable there for this to happen. The logic here might be a little bit confusing, but I guess if you draw a picture it will be better explained. So we will have the j nodes, the second nodes that we're looking at, have its previous pointing to the current I, and store the nodes i's next in a temporary variable there, and have the I points to the j's next, and have the j's next pointing to the temporary. One complicated that we might need to deal with is that what if the previous I is actually the null pointer, so that node I is the very first node. We need to update the head alias as well. So that's swapping. It's also bottlenecked by the traversal, so it's a linear time operation to swap two nodes by their index. Very lastly, the common operation is to do the reversal of linked list. It's pretty much just similar to the swapping. We rewiring any kind of this swapping or reversal. It's rewiring those next reference pointer. So what we do for every given node, we try to look at the next node in line, have that change my current next pointer. Instead of pointing to this previous next, we're gonna pointing to the previous, and have the previous node pointing to the change the reference to the previous node to the current node, and have the current node points to the next that we got. So these two lines here, the last two lines here, are advancing and these previous two lines here are this second line inside this while loop is to do the actual rewiring, reverse the pointer ordering, and in Python you can actually do this in one line. I'm not entirely sure about the readability of this. I have trouble understanding how the links is rewired when I just look at this one-line assignments. Again, drawing a picture, and works through a concrete example, we'll be able to make sure that this operations actually is the correct one. It's usually really beneficial to draw a picture. Otherwise, it will be easy to got confused and have the code not working. The common problems that I can recall is that usually in these 5 kind of categories. One is two pointers. We either have a left and right pointer. Maybe the sequence of nodes represents some kind of a symmetric kind of pattern. We want to detect that. That's something like a palindrome in the linked list. Also, there might be the slow and fast pointers. We can have 2 pointers to traverse the same linked list at the same time to detect maybe if we have cycles or not. If we have cycle, the slow and fast pointer will meet each other at certain time points. So if they never meet each other and the fast reach the end, that means there is no cycle. If they actually meet, it's indicative of a cycle. And based on how fast and slow those 2 pointer advance in this sequence, linked list the sequence, we can actually identify the starting point for the cycle. Doing a lot of interesting stuff like how long is the cycle and those. And the other is to find the last k elements from the right hand side. If we have a double linked list, it's easy, but if we have single linked list, we're going to use the 2 different pointers. Have the faster one they're going to be not necessarily faster and slower. They're going to move in the same speed, but have one pointer to move k times ahead of time, so that once the faster reach the end, the slow one will be pointing to the nodes that we want. And the second category is we have multiple kind of linked list, and we want to do some kind of merging or intersection. So it's also multiple pointers. They're gonna traverse in the the multiple linked list simultaneously. We're gonna either choose to grab one from one of those based on some condition, or just advancing them in the same time and processing at the same time, something like that. The third category is searching and sorting. We want to find some numbers, or we want to sort the objects, the nodes objects in the linked list. And the sorting usually is kind of in place, so rewiring those pointers instead of creating new copies of the nodes. And the fourth category is to use linked list as the underlying data structure to implement stack, queue, DAG, those type of thing. And very lastly will be the coupling of double linked with hash table to implement something that's you want constant access to the data objects, but also want to maintain a sequential order. Something like least recent used cache, ARU cache, is fall into this category. Yeah, so that's pretty much the quick the summary of linked list. And I'm gonna pick. I think I'm gonna pick questions representative for those categories, and maybe group some together to make a video about on one day, and move to the next kind of category. Find the really classical question for that category in the next day. So yeah, we expect some more questions about linked list to come this week. Alright, so that's it for today. Happy whatever Memorial Day, if that's the holiday you celebrate, I guess.